Okay, so we have this I. So if I now integrate this one, this is nothing to integrate, of course. If I integrate by parts, so these terms integrating by parts, we get minus h to h phi minus zeta d2 phi dy to dy equal to a case as okay, let me write the full way, d phi dy, and this is minus h to h minus h to h 1 into d phi dy whole square dy. So this is 0 because phi is 0 in both plus h and minus h. So this is nothing but and this is 0. So what I get is minus h to h d phi dy whole square dy. Now d phi dy whole square, phi is known in quasi-parabolic terms. So this becomes a integration. If I substitute the phi value quasi-parabolic ky by quasi-parabolic kh, so this becomes minus h to h sine hyperbolic square kappa y dy. This is not k, we have defined as kappa because kappa is the inverse of the ideal thickness. Okay, so if I now simplify this one, so this is becoming minus zeta square kappa square by cos hyperbolic kh. So if you do the little simplification, this will come as sine hyperbolic 2 kappa h by 2 kappa minus h. So I becomes E0 into 2h nu bar average conductivity plus there is a minus, so this is plus zeta square by mu h into, right in this way, sine hyperbolic 2 by epsilon. If I now introduce a epsilon, which is nothing but 1 by kappa h by 2 by epsilon minus 1 by epsilon square cos hyperbolic epsilon. Okay, where epsilon I have just introduced here, epsilon equal to lambda by h. So that means, in other words, this is 1 by kappa h. So if I have the lambda to be very thin, so epsilon tends to 0. Okay, so that is epsilon tends lambda tends to lambda many times less than h implies epsilon tends to 0. So in this situation, what we'll have from here, that this term will reduce to 1, and what we get is I nothing but, if instead of that is, let us write if. So in that case, what I get is twice h E0 nu bar. And also the nu bar, what we have defined before, so is also, if I have the, when ideal is thin. So this nu bar is also something like nu. Already we have defined that. So this I becomes 2h E0 f square by RT d into 2C0, because there are ionic concentration become 2C0, as 2C0 is sigma Zi. So this is under for an electrically neutral situation. Case, or that means in the electrically neutral bulk fluid or on the core fluid. So that is normally the case if you have lambda is many times less than h. So this is the way the in the slip model, free slip model, which we have introduced previously, calculate the average current density. So average current density per unit width and also per unit height, if I now divide by 2h, so that becomes a constant value. Now, so if I define a, here there are several simplification we have taken, that the diffusivity constants are taken to be same for both the ions. So, and also we have taken into consideration that Zi Ni equal to 0 because of the electroneutrality. Now, if I consider a characteristic current density I0, if I define by this manner, 2C0 dF by H is the characteristic current density. So, now here we note that phi 0 is RT by F, the thermal potential, and that is become the scale for this E0 or the electric field. So, then I0 is the characteristic current density, and phi 0 by H is the scale for electric field. So, if I introduce this, so what I find is I, a scaled I, that becomes 1 by I0 into E0 by phi 0 by H. So, this is becoming the I by 2H. Okay. So, we get a situation for under the electroneutral condition. Here, of course, we have assumed that the molecular diffusion coefficients are identical for both the ions. So, this is all about the situation where we have considered the current density and electric field and velocity and all, where the ions are taken to be symmetrical and governed by the equilibrium situation. And also another important thing we have assumed is that we have considered the binary electrolyte. So, that means symmetric binary electrolyte. Now, if it is not a symmetric binary electrolyte, so in the asymmetric case, say here we have restricted our attention on electrokinetics of binary symmetric Z-Z electrolyte. However, electrolyte can have asymmetric ions. In that case, the ionic strength are not exactly equal to the C0. So, this becomes a complicated situation, and we cannot have a Poisson-Boltzmann model. Poisson-Boltzmann equation will not appear. So, our next topic is to construct the Nernst-Planck model for Nernst-Planck model in for EOF in a slit channel. We are still considering the simple geometry, simple configuration. So, that means you have the situation like this way. You have a electric field, and this is along x axis, along the direction of the axis we have considered, and both the walls are taken to be same zeta potential. Of course, we can switch to some other case also. That means we can have a different zeta potential. That is not a, that change switch over is not a very big amount of trouble will cause. So, we are considering a parallel flow. Of course, that is u is a function of y and v is 0. So, what you have here, the momentum equation is mu d to u dy 2 equal to rho e del phi del x. So, that means this is the balance of the viscous diffusion and the electric body force. Now, phi, as we have already stated, this is E0 x plus phi y, which is the as this, because we are considering a fully developed situation. So, and also we have taken a symmetric electrolyte, not yet symmetric electrolyte. So, this is the induced potential. So, with that, what we can write is mu d2u dy 2 equal to minus E0 f sigma j di Ci, the rho e. Del phi del x gives you this minus E0. Now, for the simplicity will come later on. So, the transport equation for the ith ionic species can be written, because again fully developed. So, all the gradient with respect to x are 0. So, del Ci del y plus Zi Fy RT Ci del phi del y equal to 0. So, this is one equation, say A, this is equation B, and also the, so this is I equal to whatever situation you are considering, because in the Boltzmann distribution we are not restricting like Boltzmann distribution. So, also the Poisson-Boltzmann equation, we have we must have the symmetric electrolyte consideration, and this supplemented by the equation for electric field. or the electric potential. So this can be written as d2 phi dy 2 equal to minus 1 by epsilon E f sigma j I Ci. So these equations basically are known to us. Now, how we impose the boundary condition. So basically, we need to solve this set of equations for if we don't go by the assumption that CIs are governed by the Boltzmann equation and the number of ionic species are symmetric and binary. So that kind of assumption, if you are not imposing, so any kind of situation, say I equal to 1 to n, so you have a situation like this way. Now, so these are the equation ABC. So these equations are for number of ionic species. So they are coupled. One, what we can see is that we can't solve it individually. So one solution is depending on the other. So we can have to impose the boundary conditions. So on the boundary, what conditions we can impose on the boundary? So we impose no normal flux of ion, and no normal flow of fluid. In other words, the boundaries are assumed to be unpenetrable and rigid. So if we assume this kind of situations, so what I get here, that on the boundary we can have a situation as on y equal to 0, and if I take the other one as h, so you have the u equal to 0 because u is the velocity slip, here is the no slip. So fluid velocity, we impose no normal flux of ions and no fluid flow of fluid. So normal flow is 0, and also to the viscous flow, the condition that no flow of fluid. So u equal to 0 and nci dot y, here is the vector. So this is equal to 0. So this gives you u equal to 0, and the other conditions what we have is dci dy plus j di ci minus, I guess, d phi dy equal to 0. There will be plus. There was a minus over there, so it should be plus, I guess. Yeah. So yeah, this will be plus. So this is the for I equal to whatever 1, 2, etc. And you have phi equal to zeta on y equal to 0 and h, or you can have the condition of charge density, that is d phi dy equal to minus sigma s by epsilon e on y equal to 0 and h, where sigma s is the surface charge density of the non-conducting surface, above which, or non-conducting liquid surface interface. liquid solid interface. Now, if it is a perfectly conducting, so in that case we can impose a condition as phi equal to zeta, or zeta can be prescribed. So, on this rigid surface itself. So, these are the boundary conditions one has to impose for phi. This is the conditions for Ci. This is the condition for the velocity. So, these boundary conditions are complete because we have a second order ordinary differential equation and we have the governing boundary conditions. So, this set of equations along with this boundary condition cannot be solved in a analytic fashion, obviously, and also things becomes complicated if you have the number of ionic species are increased. Okay, and these boundary conditions can also be little simplified. That means, since we are taking this is a 0 and u is 0, so one can assume a Boltzmann distribution on the surface itself. Only assume the Boltzmann distribution along the surface. Now, let us consider for simplicity a situation where for simplicity we consider the Norris plug model for a binary, let us take monovalent electrolyte. So, in other words, you have Z1 equal to minus Z2 equal to 1, and let G and F are the mole fractions of cations and anions. What is G and F? That is G equal to Ci by C0 and or rather C1 by C0 and F equal to C2 by C0. C0 is the bulk ionic concentration. So, in terms of the mole fractions G and F defined this way, so you can rewrite the equations whatever we have derived, the governing equations can be expressed as d2u dy2 equal to minus kappa h g minus kappa h whole square g minus f, and d dy of dg dy minus plus g d phi dy equal to 0 and d dy of df dy minus f d phi dy equal to 0, and along with the electric potential equation, that is d2 phi dy2 equal to minus kappa h whole square g minus f. Now, here what we did is we have taken the u. Here u is scaled by U0 and kappa was introduced. So, kappa in this case is, since we are taking a symmetric binary electrolyte, so this will be the ionic concentration is C0. So, but if it is not a symmetric electrolyte, so we will have the ionic concentration is different from C0. So, U0 we have taken as epsilon E0 phi 0 by mu. So, basically this is a Smolchowski velocity with surface potential as phi 0. So, this is the thing is considered to be the velocity scale. Here U is scaled by phi 0, the electric potential phi is scaled by phi 0, which is nothing but T by F, the thermal potential scale, and Y is scaled by H. Okay. And the kappa Y is scaled by H, and kappa, which is nothing but the inverse of Debye length, is F square C0 to C0 by epsilon E RT. Now, if it is not a binary electrolyte, in general, so kappa is, I would say, so this is to the power half to F square sigma J squared Ci by epsilon E RT to the power half. Now, in this case, if we have a symmetric binary electrolyte, so we can have a this one is equal to 2C0, but otherwise there will be a parameter has to be introduced, as we have discussed before. The ionic concentration may not be the same as 2C0. So, another thing is that from here that the equation for phi, equation for U and phi are identical, but however, their boundary conditions are not same. So, these equations for U and phi are identical, and also we have the boundary conditions we can write as y equal to 0 h, we have U equal to 0, dg dy plus g d phi dy equal to 0, f dy minus g d phi dy equal to 0, and the conditions for phi, so phi equal to zeta or d phi dy, or you may have this one d phi dy equal to minus d phi dy equal to minus sigma s by epsilon e. So, one need to solve this coupled set of equations by some numerical technique. Okay, so we will carry to the next lecture.